Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to talk about valence bond theory. When we think about chemical bonding, our goal is to understand how atoms come together to form molecules. Over time, chemists have developed different models to explain bonding, with each one addressing the limitations of previous models. Today, we're going to walk through the progression of bonding models, starting with a review of Lewis structures and VSEPR theory, and we're going to let the limitations of those models lead us to valence bond theory. From there, we're going to explore how this model helps explain molecular bonding, but we're also going to highlight its limitations, which will ultimately lead us to molecular orbital theory in the next lecture. Let's start with Lewis structures. This is one of the simplest ways to represent chemical bonding. Lewis structures help us keep track of valence electrons. These are the outermost electrons that are responsible for bonding. By drawing dots and lines, we can visualize how atoms share electrons to achieve a stable electron configuration, following the octet rule for most elements. This model is useful because it allows us to predict how atoms are connected in a molecule and whether those connections involve single, double, or triple bonds. However, there is a major limitation. Lewis structures are two-dimensional representations, but real molecules, they exist in three-dimensional space. So the way we draw them on paper doesn't tell us the actual geometry of a molecule. To address this, we introduced VSEPR theory. This model helps us predict the three-dimensional shape of molecules based on the idea that electron pairs repel each other and they arrange themselves to minimize repulsions. VSEPR allows us to determine whether a molecule is linear, trigonal, planar, tetrahedral, or it adopts another shape based on the number of bonding and lone pairs around the central atom. This is an improvement over Lewis structures because it gives us geometrical insight into molecular structure. At this point, we've made significant progress. We now know which atoms are connected because of Lewis structures, and we know the shape they form because of VSEPR theory. However, neither of these models explain what actually happens at the atomic level when atoms come together to form bonds, how atomic orbitals contribute to bonding, or why certain bonds are stronger or more stable than others. This is where valence bond theory comes into play. Valence bond theory builds on what we know by explaining bonding at the atomic orbital level. It describes bonding as the overlap of atomic orbitals. Instead of representing bonds as simple lines like in Lewis structures, valence bond theory tells us that bonds form when atomic orbitals from two atoms overlap and share a pair of electrons. And this approach helps explain why some bonds are stronger than others, depending on how much the orbitals overlap. For example, let's take a look at H2. In H2, or dihydrogen, each hydrogen atom has a 1s orbital with a single unpaired electron. When two hydrogen atoms come together, their 1s orbitals are going to overlap to form a strong and stable covalent bond. Now, for a simple molecule like dihydrogen, valence bond theory works really well in explaining how these atomic orbitals overlap to form bonds. However, this approach doesn't always explain bonding in more complex molecules. The reason is that an atom's strict atomic orbitals, SPDF, don't always align with the bonding geometries that we observe experimentally. This is where things change up on us a little bit, and it brings us to an important point about scientific models. A model in chemistry is not an absolute truth, but rather a simplified way of describing observations. When a model works well, we use it to make predictions. However, when we find cases where the model doesn't fully align with the experimental data, we modify or refine it. This is exactly what happens as we move from Lewis structures to Vesper theory to valence bond theory and eventually molecular orbital theory. Each model adds a new layer of understanding that helps us refine our ability to describe bonding in greater detail. So, to address the discrepancy between atomic orbitals and observed molecular shapes, we introduce the idea of hybridization. This concept explains how atomic orbitals can mix together to form new orbitals that better align with molecular bonding geometries and explain those experimental observations. To introduce hybridization, we'll explore examples that demonstrate why it is necessary, starting with a molecule called methane, CH4. And here we're going to see why atomic orbitals alone don't seem to account for the bonding we observe. And through these examples, methane being the first one, ethylene and acetylene is something else we're going to cover. We're going to see why hybridization is essential for a complete understanding of bonding. With that being said, let's begin our discussion of hybridization by analyzing what happens in methane, CH4, and why carbon forms four equivalent bonds despite carbon's electron configuration suggesting otherwise. If we look at carbon's ground state electron configuration, it is 1s2, 2s2, 2p2. This means carbon has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then 2 unpaired electrons in the 2p orbitals. Based on this configuration alone, you might expect that carbon's going to form only 2 bonds, one with each of these unpaired electrons. However, experimental evidence tells us something different. Carbon actually forms 4 identical bonds in methane in CH4, each with the same bond energy and with the same bond length. More importantly, methane adopts a tetrahedral shape, meaning its 4 bonds are arranged symmetrically in 3-dimensional space with bond angles of approximately 109.5 degrees. So how can we explain this? The answer lies in hybridization. This is a theoretical model that's used to describe atomic orbitals in a way that aligns with the observed bonding geometry. Hybridization is not a physical process that atoms undergo, but rather a mathematical model that helps us understand bonding better. The mathematical background for hybridization comes from the linear combination of atomic orbitals. This is a principle in quantum mechanics. In simple terms, hybrid orbitals are generated by taking weighted sums of atomic orbitals to produce new orbitals that better describe molecular bonding. In the case of sp3 hybridization, carbon's 2s orbital and 3 of its 2p orbitals mathematically combine to form 4 identical sp3 orbitals. These new orbitals are degenerate, meaning they all have the same energy, and they arrange themselves tetrahedrally to minimize electron repulsions, which aligns perfectly with the experimentally observed structure of methane. So this model explains why all 4 of the carbon-hydrogen bonds in methane are identical, even though carbon's ground state electron configuration initially suggests otherwise. Another key feature of sp3 hybridization is that these hybrid orbitals have 25% S character and 75% P character. This means they retain some of the properties of both S and P orbitals, but they are distinct from the original atomic orbitals. The increased P character influences the bond angles, and it ensures they match the experimentally observed 109.5 bond angles in tetrahedral molecules like methane. So in summary, the concept of hybridization allows us to explain why carbon forms 4 equivalent bonds instead of 2, and why methane adopts a tetrahedral shape. Without hybridization, valence bond theory alone would struggle to account for these observations. Now that we've introduced sp3 hybridization in methane, let's move on to another important type of hybridization, sp2. To understand this, we're going to look at C2H4. This is a molecule where each carbon is bonded to 3 other atoms, 2 hydrogens and 1 other carbon, while also forming an additional interaction between those 2 carbons because there's a double bond between them. Again, if we consider carbon's ground state electron configuration, we might assume that each carbon can only form 2 bonds since there are only 2 unpaired electrons in the 2p orbitals. However, we know from experimental data that each carbon in C2H4 forms 3 equivalent bonds in a trigonal planar shape with bond angles of approximately 120 degrees. This presents a discrepancy. Carbon appears to form more bonds than we would expect from its atomic orbitals alone. So to explain this, we again apply hybridization, which allows us to describe how carbon's atomic orbitals combine to create a new set of orbitals that better match the molecule's observed bonding geometry. In sp2 hybridization, one of the 2s orbitals, there's only one, and just two of the 2p orbitals mix together and they form 3 new sp2 hybrid orbitals. These hybrid orbitals are equal in energy, so they're degenerate, and they arrange themselves 120 degrees apart in a trigonal planar geometry, which minimizes electron repulsions. This explains why each carbon in C2H4 forms 3 equivalent bonds in a flat planar structure. However, unlike sp3 hybridization, where all 3p orbitals are involved in hybridization, sp2 hybridization leaves 1 p orbital unhybridized. This remaining unhybridized 2p orbital is going to be oriented perpendicular to the plane of the molecule, and it does not participate in the 3 equivalent bonds. Instead, this orbital allows for an additional bonding interaction between the 2 carbon atoms, which contributes to the double bond that we see here in C2H4. So this is an important distinction. Unlike in methane, CH4, where only single bonds are present, the presence of an unhybridized p orbital allows C2H4 to form a stronger connection between its 2 carbon atoms. Another important characteristic of sp2 hybridization is its orbital composition. Since we have 1 s orbital and 2 p orbitals mixed together, each sp2 hybrid orbital consists of 33% s character and 66% p character. The higher p character influences the bond angles, and it ensures that each carbon forms about a 120-degree bond angle, which is consistent with our experimental observations. Now, let's move on to the last type we'll cover in detail, and that is sp hybridization. To understand this, we're going to examine acetylene, C2H2. This is a molecule where each carbon forms a single bond to a hydrogen and a triple bond to the other carbon. If we consider, again, carbon's ground state electron configuration, we might initially expect that each carbon can only form two single bonds using its two unpaired p electrons, but we know from experimental data that acetylene has a linear shape with a bond angle of 180 degrees, and that the carbon-carbon bond is much, much stronger than a typical single bond. So that suggests that additional bonding interactions are taking place. To explain this, we once again apply hybridization, which allows us to describe how carbon's atomic orbitals combine to match the observed molecular geometry. In sp hybridization, one of the two s orbitals and one of the two p orbitals mix together and they form two new sp hybrid orbitals. These orbitals are degenerate. That means they have equal energy and they arrange themselves 180 degrees apart to minimize electron repulsions. And that explains the linear structure of acetylene. Now, unlike sp2 hybridization, where one p orbital remains unhybridized, sp hybridization leaves two p orbitals unhybridized. These two remaining p orbitals are going to be oriented perpendicular to each other, and they participate in additional bonding interactions between the two carbon atoms. And this contributes to the formation of this triple bond in acetylene. So looking at the trend so far, we see that the number of unhybridized p orbitals corresponds to the number of additional bonding interactions. In sp3 hybridization, no unhybridized p orbitals remain, so it leads to only single bonds. In sp2 hybridization, one unhybridized p orbital allows for a double bond. In sp hybridization, there are two unhybridized p orbitals that allow for a triple bond. And this explains, again, why acetylene has a linear shape and it contains this strong carbon-carbon triple bond. Another defining feature of sp hybridization is its orbital composition. Since we have one s orbital and one p orbital mixed together, each sp hybrid orbit consists of 50% s character and 50% p character. Again, each sp hybrid orbital consists of 50% s character and 50% p character. Now, the increased s character means that sp hybrid orbitals hold their electron density closer to the nucleus, resulting in shorter and stronger bonds. So this is another reason why the carbon-carbon bond in acetylene is so strong. Now that we've explored different types of hybridization through examples like CH4, C2H4, and C2H2, let's take a step back and tie everything together. We've seen that valence bond theory explains bonding through the overlap of atomic orbitals, but we also discovered that pure atomic orbitals don't always match the geometries we observe in molecules. Hybridization is the model that helps bridge this gap. It allows us to describe bonding using new hybrid orbitals that align with molecular geometry predictions. This brings us to an important question. Can we generalize hybridization? In other words, now that we've seen specific cases, can we apply a general rule to predict hybridization in any molecule? And the answer is yes. The key to predicting hybridization lies in counting electron-rich regions around an atom, which includes bonds and lone pairs, and the number of these regions determines the type of hybridization the atom undergoes. Let's take a look at this table and break it down. If an atom has two electron-rich regions, it adopts sp hybridization. Because the two sp hybrid orbitals arrange themselves 180 degrees apart, we get a linear molecular geometry. When an atom has three electron-rich regions, it undergoes sp2 hybridization. Here, one s orbital and two p orbitals mix, leaving behind one unhybridized p orbital that allows for additional bonding. The three sp2 orbitals arrange themselves 120 degrees apart, leading to a trigonal planar molecular geometry. If we increase to four electron-rich regions, the atom adopts sp3 hybridization, just like we saw in methane. We have one s orbital and three p orbitals mix to create four identical sp3 hybrid orbitals, which distribute themselves approximately 109.5 degrees apart in a tetrahedral geometry. Now, what happens when we move beyond four electron-rich regions? For molecules with five electron-rich regions, we introduce d orbitals into the mix, and this leads to something called dsp3 hybridization. This occurs in molecules like phosphorus pentachloride, where five hybrid orbitals arrange themselves into a trigonal bipyramidal shape. Finally, when an atom has six electron-rich regions, it undergoes D2 sp3 hybridization, meaning that two d orbitals, one s orbital, and three p orbitals combine to form and create six equivalent hybrid orbitals. This results in an octahedral geometry, which we see in molecules like sulfur hexafluoride. So, by simply counting the number of electron-rich regions around an atom, we can predict its hybridization. With that, let's tackle some practice problems. This first one says, how many and what kind of atomic orbitals are needed to hybridize to form a molecule with trigonal planar geometry? We just learned that hybridization depends on the number of electron-rich regions around an atom. If a molecule has trigonal planar geometry, this means there are three electron-rich regions surrounding the central atom. From our generalization of hybridization, we know that three electron-rich regions correspond to sp2 hybridization. This means that the central atom must form three sp2 hybrid orbitals, which are created by mixing one s orbital and two p orbitals. That means that the correct answer here is going to be answer choice C. The next problem says, identify the hybridization of atoms 1, 2, and 3 in that order. So this is atom 1. It's a carbon atom. This carbon is double bonded to another carbon, and it is single bonded to two different hydrogens. So this carbon is surrounded by 1, 2, 3 electron-rich regions, and this corresponds to sp2 hybridization. Let's look at atom 2. It's another carbon. This carbon is double bonded to a carbon, single bonded to a hydrogen, and single bonded to another carbon. So again, this carbon is surrounded by 3 electron-rich regions. This corresponds to sp2 hybridization. Finally, atom 3 here is an oxygen atom. This oxygen atom is double bonded to a carbon, and it has 2 lone pairs. This means this oxygen has 3 electron-rich regions, so it is also sp2 hybridized. Therefore, the correct answer is D. This final question here says, which of the following statements are true regarding the molecule below? Statement 1 says, there are 5 sp2 carbons and 3 sp3 carbons. So let's work through each carbon, count the number of carbons that are involved in double bonds versus those involved in single bonds, and that's going to help us determine whether there are, in fact, 5 sp2 carbons and 3 sp3 carbons. So whenever we see a carbon like this, we notice it has 2 single bonds and a double bond. This carbon is sp2 hybridized. Same thing with this carbon, 3 electron-rich regions, and one of them is a double bond. This is sp2 hybridized. This carbon also is surrounded by 3 electron-rich regions. It's sp2, and the same goes with these 2 carbons as well. So far that's 5 sp2 carbons. Let's see if there's any more, or maybe the rest of the carbons are sp3. We don't know. Let's look. This carbon is surrounded by 1, 2, 3, 4 electron-rich regions. So this carbon right here is actually sp3. Same goes with these 2 carbons because they're both also surrounded by 4 electron-rich regions. So what that means is we have 5 sp2 carbons and 3 sp3 carbons. This statement is true. Statement 2 says there are no sp3 carbons. We've already determined that 3 of the carbons are in fact sp3 hybridized, so this statement is false. Our final statement is that there are 4 sp carbons. We do not see any carbons here that are only surrounded by 2 electron-rich regions, which is what would classify it as an sp carbon. So that means this statement is also false. The only statement that's correct is statement 1, so A is the correct answer choice here. Now that we've developed a strong understanding of hybridization, let's take a closer look at the 2 fundamental types of covalent bonds. Those are sigma bonds and pi bonds. These 2 bonding types describe the different ways atomic orbitals overlap to form covalent bonds, and understanding their distinctions will help us explain single, double, and triple bonds. A covalent bond is formed when atomic orbitals from 2 atoms overlap and they allow their electrons to be shared. However, not all bonds form in the same way, and there are only, again, 2 types of bonding interactions we need to know, sigma and pi bonds. The key difference between them is how the atomic orbitals overlap. A sigma bond forms when 2 atomic orbitals overlap head-on, meaning their electron density is concentrated directly along the bond axis. This is a straight line connecting the nuclei of 2 bonded atoms. Because this direct overlap maximizes electron density between the nuclei, sigma bonds are the strongest type of covalent bond. Sigma bonds can be formed through different types of orbital overlap. You can have an S-S overlap. You have 2 s orbitals overlapping like we saw in H2 or dihydrogen. You can also have an sp overlap, an s orbital overlapping with a p orbital. Or you can have 2 p orbitals overlapping head-on. In addition, you can have hybrid orbitals overlap, such as sp or sp2 or sp3. They can overlap along the bond axis. Regardless of whether a bond is a single, double, or triple bond, every bond contains exactly 1 sigma bond. Single bonds are purely sigma bonds, while double and triple bonds contain additional bonding interactions that we're going to discuss now as we transition into pi bonds. A pi bond is different from a sigma bond because it does not form from head-on overlap. Instead, it occurs when two unhybridized p orbitals overlap sideways, creating regions of electron density above and below the bond axis. Since the overlap in a pi bond is not as direct as in a sigma bond, pi bonds are weaker than sigma bonds. Pi bonds only form in double and triple bonds. A double bond is going to consist of one sigma bond and one pi bond. A triple bond consists of one sigma bond and two pi bonds. This additional bonding explains why double and triple bonds are stronger and shorter than single bonds. The extra electron density from pi bonds increases attraction between atoms. Now that we know how sigma and pi bonds form, there's a simple way to identify them in a molecule. Again, a single bond always consists of just one sigma bond. A double bond consists of one sigma bond and one pi bond. And a triple bond consists of one sigma bond and two pi bonds. No matter how many bonds exist between two atoms, only one of them is a sigma bond, while the rest are pi bonds. Now that we've developed this solid understanding of sigma and pi bonds, as well as how hybridization determines the orbitals involved in bonding, let's go through a systematic approach for analyzing bonds in any given molecule. Our goal is to identify both the type of bond, is it sigma or pi, and the atomic orbitals that are involved in forming that bond. So to break this process down, there are four key things to keep in mind. If you're starting from the very beginning, you're not given much information, the first thing you want to do is draw the Lewis structure. This is going to provide a clear representation of which atoms are bonded and how many bonds exist between them. Then you want to determine the hybridization of each atom. We do this by identifying electron-rich regions, which tell us which hybrid orbitals are involved. Then we want to classify each bond as sigma or pi. Recall that every single bond is a sigma bond, while double and triple bonds contain additional pi bonds. Then we want to be more specific, and we want to assign atomic orbitals to each bond. Sigma bonds form from overlapping hybrid orbitals or atomic orbitals, while pi bonds always come from unhybridized p orbitals. In order to complete step 4 appropriately, I also want you to keep in mind that hydrogen is always contributing the 1s orbital when it bonds, since it only has one electron in its first energy level. For other atoms, hybridization is assigned based on electron-rich regions like we've discussed thus far. Of course, this is best understood by tackling some practice problems. This first one says, what types of sigma and pi bonds exist between C1 and C2? What about C2 and C3? Let's take a look at C1 and C2 first. They share a triple bond. C1 and C2 are both surrounded by two electron-rich regions. That means they're both sp hybridized, meaning each has two sp orbitals for sigma bonding, and they have two unhybridized 2p orbitals for pi bonding. Then let's look at C2 and C3. C2 we already said is sp hybridized because it's just surrounded by 2 electron-rich regions. But C3 is surrounded by 4 electron-rich regions. So it is sp3 hybridized, meaning it has 4 sp3 orbitals for bonding. Now let's classify the sigma and pi bonds at play here. This triple bond between C1 and C2 consists of 1 sigma bond and 2 pi bonds. The single bond between C2 and C3, that consists of just 1 sigma bond. But this isn't enough information. We need to connect these ideas together and assign atomic orbitals. So the sigma bond that is between C1 and C2, that results from sp-sp orbital overlap. So we don't want to just write 1 sigma bond. It's specifically 1 sigma bond between the sp orbitals of both carbon 1 and carbon 2. What about the 2 pi bonds between C1 and C2? They result from the sideways overlap of the unhybridized 2p orbitals. So specifically, these 2 pi bonds that happen between C1 and C2, they're specifically pi bonds between the 2p unhybridized orbitals of both carbons. Finally, we want to be more specific about the sigma bond between C2 and C3. The sigma bond results from the overlap of the sp orbital from C2 and the sp3 orbital from C3. So this sigma bond is specifically a sp-sp3 orbital overlap. And with that, we've completed both of these practice problems and all of the topics we wanted to cover in this lecture. In the next lecture, we're going to start talking about molecular orbital theory. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.